Hello, my name is Austin Bingham. Welcome to the fourth module of the Python Fundamentals course, where we seek to understand the Python object model, take a more in-depth look at some collection types we've met already, and introduce a few more collection types. We've already talked about and used variables in Python, but what exactly is a variable? What's going on when we do something as straightforward as assigning an integer to a variable? In this case, Python creates an int object with a value of 1000, an object reference with the name x, and arranges for x to refer to the int 1000 object. If we now modify the value of x with another assignment, what does not happen is a change in the value of the integer object. Integer objects in Python are immutable and cannot be changed. In fact, what happens is that Python creates a new immutable integer object with the value 500 and redirects the x reference to point at the new object. We now have no way of reaching the int 1000 object, and the Python garbage collector will reclaim it at some point. When we assign from one variable to another, we're really assigning from one object reference to another object reference, so both references now refer to the same object. If we now reassign x, we have x referring to an int 3000 object and y referring to a separate int 500. And there is no work for the garbage collector to do, because all objects are reachable from live references. Let's dig a little deeper using the built-in id function, which returns an integer identifier which is unique and constant for the lifetime of the object. Let's rerun the previous experiment using id. Note that the id function is seldom used in production Python code. Its main use is in object model tutorials such as this one and as a debugging tool. Much more commonly used in the id function is the is operator, which tests for equality of identity. That is, it tests whether two references refer to the same object. We've already met the is operator earlier in the course when we tested for none. Even operations which seem naturally mutating in nature are not necessarily so. Consider the augmented assignment operator. Now let's look at that pictorially. We start with t referring to an int5 object. Augmented assignment creates an int2 without assigning a reference to it. It then adds the original int5 with the new int2 to produce a new int7. Finally, it assigns t to the int7 and the remaining ints are garbage collected. Python objects show this behavior for all types. The assignment operator only ever binds to names. It never copies an object by value. Let's look at another example using mutable objects, lists. We create a list object with 3 elements, binding the list object to a reference named r. Then assign r to a new reference s. When we modify the list referred to by s by changing the middle element, the r list has changed too, since the names s and r in fact refer to the same object. Let's see that again with a diagram. First we assign r to a new list. We then assign s to r, creating a new name for the existing list. If we modify s, we also modify r, because we're modifying the same underlying object. S is r is true, because both names refer to the same object. If you want to create an actual copy of an object, such as a list, other techniques must be used, which we'll look at later. It turns out that Python doesn't really have variables in the metaphorical sense of a box holding a value. It only has named references to objects, and the references behave more like labels, which allow us to retrieve objects. That said, it's still common to talk about variables in Python. We will continue to do so, secure in the knowledge that you now understand what's really going on behind the scenes. Let's contrast that behavior with a test for value equality, or equivalence. We'll create 2 identical lists. Here we see that p and q refer to different objects, but that the objects they refer to have the same value. Of course, an object should always be equivalent to itself. Here's how that looks pictorially. We have 2 separate list objects, each with a single reference to it. The values contained in the objects are the same, that is, they are equivalent, or value equal, even though they have different identities. Value equality and identity are fundamentally different notions of equality, and it's important to keep them separate in your mind. It's also worth noting that value comparison is something that is defined programmatically. When you define types, you can control how that class determines value equality. In contrast, identity comparison is defined by the language, and you can't change that behavior.